Thank you for watching our presentation. Today I'll be talking about our paper, Attacks on Visualization-Based Malware Detection, Balancing Effectiveness and Executability. This work is the result of a collaboration between myself, Jingyu Qian, Tran, and Berkay Kaplan. Previous work found techniques to convert binaries into images, both grayscale and RGB, and simply run these through an image classifier for malware detection. Like other image classifiers, these models are prone to adversarial example attacks. But these attacks have limitations. First, the proposed attacks are easily filtered out because they are placed in constrained places, such as the headers or appended to the end of the binary. Second, they do not ensure executability. This especially happens when the adversarial example is generated directly from the image. In this work, we propose an algorithm that generates adversarial examples that evade image-based ML models for malware detectors, but also maintain code functionality and ensure executability. When designing our solution, we focused on the two major limitations from our literature review. First, we wanted to ensure that the added perturbations would not be easily removed through pre-processing. We achieved this by inserting the perturbations to the code section of the binary. Second, to maintain code functionality while also ensuring executability, we only utilize additive changes through adding instructions, such as no-ops. Additionally, to avoid no-op detection, we construct a dataset of instruction sequences that do not cause any functional change. We call these semantic no-ops. These will then be used to perturb the image and can be easily inserted without being detected. This is an overview of our system. In phase 1, we construct the malware detection model based on models that are described in previous work. In phase 2, we design the algorithm that generates robust adversarial examples. Each of these phases will be described in detail in the next slides. In phase 1, we replicated the malware detection model from previous papers based on their described parameters. Our model is a CNN-based image classifier with 2 convolutional layers, 3 fully connected layers, and ReLU activation functions. Our training and testing datasets were constructed by combining 2 datasets. For the malware samples, we used the MalImage dataset, a public dataset from the Vision Lab at UC Santa Barbara. For the benign samples, we used the Architecture Object Code dataset. Since the 2 datasets are in different formats, namely images and binaries, we needed to freely switch between the 2 in order to produce adversarial examples. We also developed some simple binary to image and image to binary tools to transfer between the 2 formats. Our model was able to achieve an accuracy of 100% for benign samples and 99% for malware samples. This is an overview of the adversarial example generation algorithm. This process is comprised of 4 modules: the mask generator, the adversarial example generator, the NOP generator, and the adversarial example optimizer. In the next few slides, we will be talking about each of these modules in details. Since we would like to insert no-ops to the code sections, the mask generator creates these spaces by expanding the binary. To do so, we design the mask generator. This module takes in the malware sample, the size of the perturbation allowed, and the frequency of the perturbations desired. The mask generator then outputs the new malware images with the uninitialized perturbation spaces and the perturbation mask. The mask is used later to ensure perturbations only occur in spaces within the code section. After we generate the perturbation mask and the augmented malware image, we feed them to the adversarial example generator and launch a modified version of the Carlini and Wagner attack. This generates the optimal adversarial example in the image space, which causes the malware sample to be misclassified as benign by the malware detector. The modification that we introduced to the Carlini and Wagner attack is the application of the perturbation mask to further restrict the positions of the perturbations. The objective function is given as shown here in the slide. It is important to note that at this stage, the optimal adversarial example produced might not conform to the functionality of the original binary, nor is it necessarily executable. The next steps in our algorithm deal with this issue. In the next two slides, we're going to talk about the semantic no-op generation module. In this project, we do not build a comprehensive set of semantic no-ops. We choose semantic no-ops with relatively small byte length and use them as seeds to build longer semantic no-ops. We classify our semantic no-op sequences into four main categories. First, arithmetic sequences. These include instructions that either have no effect on the contents of their registers, such as add and subtract 0, or multiply and divide by 1, or sequences that nullify each other, such as increment and decrement, or negating a value twice. Second, we have movement sequences. These include jump, move, or a push and pop sequence. Third are logical sequences such as add 1 or 0, not twice, or XOR. Finally, there are some miscellaneous instructions such as the generic no-op and other flag operations. After we generate all the possible no-op seeds, we feed them to the no-op generator. We also feed the no-op generator the target size of the perturbations that we want. The no-op generator will then output a list of all viable semantic no-op sequences with the size desired. Here's an example. Assume we want to generate a semantic no-op sequence of 7 bytes, and we have a seed that is 5 bytes long, made up of push F, add 0 to register, pop F. To reach 7 bytes, we can append to it any semantic no-op sequence comprised of 2 bytes. Below are some examples. One of them is 9090, which is the generic no-op. The other is move. And the last one is push register and pop register. In this step, we build the adversarial example optimizer module, which produces a viable adversarial example that maintains the original malware functionality. The adversarial example optimizer takes in the perturbation mask, the optimal adversarial example generated from the Carlini and Wagner attack, and the list of semantic no-ops produced by the no-op generator. Next, the adversarial example optimizer locates the allowed positions for perturbations in the optimal adversarial example using the perturbation mask. Subsequently, the Euclidean distance between the instruction sequences in the allowed perturbation spaces and the semantic no-ops is calculated. This process identifies the semantic no-ops closest to each of the sequences in the allowed perturbation spaces of the optimal adversarial example. In the current implementation, this process is done sequentially for each perturbation block. After that, the semantic no-ops with the minimum distance are used to replace the perturbation blocks in the optimal adversarial example. The new adversarial example is called the optimal viable adversarial example. We also implement a fail-safe step in the case that the adversarial example fails to cause a misclassification. In this step, we use the failed adversarial example as our starting point and keep iterating until a viable successful adversarial example is found or timeout is reached. In the next few slides, we evaluate our algorithm and show the results of our experiments. We focus our evaluation on the Dial Platform B malware family. This includes 174 malware samples. The malware samples are of two sizes, 216 by 64 pixels and 432 by 64 pixels. Malware samples in this family are moderately large, with an average number of instructions of 622 instructions in the code section. This gives us more flexibility to generate optimal viable adversarial examples in a short time. Additionally, we found that there is a link between size and performance. This is discussed in further detail in our paper. Finally, we especially made sure that the malware images were correctly classified by the malware detection model. For all of the adversarial examples, the functionality of the original malware is preserved by construction, since we only instrument the original binary with semantic no-ops at the instruction boundaries. All the adversarial examples can be generated within 5 iterations of the Carlini and Wagner attack and adversarial example optimization. The running time to generate the adversarial example is given in the first figure to the right. We found the average time to be 77.8 seconds to generate the adversarial examples for malware samples with around 600 instructions, and the time overhead comes from the adversarial example optimization step. In the second figure, we plot the expansion rate in the malware samples after adding the perturbations. The figure shows that most adversarial examples incur a 35% size overhead. We were able to successfully generate adversarial examples for 172 malware samples out of a total of 174 samples. This translates to 98.9%. For the two malware that we failed to generate an adversarial example for, our algorithm workflow oscillates around the local optimum instead of a global one. In our paper, we briefly discuss two potential methods to prevent this from happening. We achieve similar results for other malware families with similar sizes of code sections. To conclude, we have designed an algorithm that generates adversarial examples that are resilient against preprocessing and maintain both executability and functionality of the malware sample. Our results show that the proposed algorithm produces successful adversarial examples that are misclassified by malware detectors. Thank you for listening. Please get in touch with any questions.